signals can be given to the particular machine so that the movement will be exactly to the right point in the right time for the right object. So these things we are going to understand in this session. You can see here human body analogy compared to human different types of robo joints it is. So how we are going to touch and how we are going to sense and how we are going to hold. And finally, especially the very common part, very simple structure of robo, if you observe, it will be robo arm, especially for pick and place. In the industries, in place of human, if you want to replace some other machine, that will be a robo arm. That is more than enough, especially in assembled
how we are
line.
going to sense
The part
and
will
how
be
we are
placed
going
and
to
it will
hold
be assembled and it will be
finally
sent to another stage of assembly operation. So especially for pick and place, for segregation of the product in the quality section and all, this robo arm is more than sufficient. So this robo arm is exactly related to our complete hand itself. You can take it from the shoulder to till fingertip. If you take it, how the structure of our human hand from the shoulder joint, elbow, then wrist, and how the finger structure. Each and everything, how if you observe it, so how the shoulder joint will be. The shoulder is connected to elbow with the upper arm. Then elbow is connected to wrist with the forearm. So lower arm. So then wrist is connected with this finger. This is called gripper. This is called gripper, or you can use it a holding device or clamps or whatever it is in different terminology for different applications. So this particular one, this complete robo arm is important, especially in any kind of industry for most of the simple applications and with the least possible budget and all. Okay, it will sense, especially for automatic applications. It will be helping us to hold the object. It will be helping us to make the movement for placing object in one place and picking the object from another place, especially for assembly operations, segregation, quality control section, and even what is it, like a delivery in the sense delivery of the product from one place to another place. So picking the right product, again placing in the right position, like a medicine delivery, that and all we can check it here. So this is simple component, especially with respect to complete robo structure, which will be useful in most of the industries for multiple applications. So that's why I have just given a human body analogy, how it can be connected to the robo structure, especially robo arm structure. So the shoulder joint, so here we can check it, the shoulder joint, elbow, and wrist. So here also it is, you can see here, this is the finger, means like the complete palm it is. This is the wrist joint, elbow joint, and shoulder joint. But here it will be in a reverse direction. So for human hand, it will be downwards, shoulder will be top, wrist will be down. But when it comes, of course, we can even lift it also. That is up to the requirement, the position of the work, the place of the work, where you are trying to work. Accordingly, we can try to, what to say, like make a movement of our shoulder. Then accordingly, hand movement will be there. Based on that, you can try to adjust your hand movement, either involving all parts of the hand or only the minimum parts of the hand to complete the particular task. So especially with respect to ergonomic structure, if you want to work, always ergonomics will always try to suggest that. So devise any product which will allow the human to complete the task with the minimum number of body parts involvement. For example, if I want to pick up something, I can, depends on the shape and size of the object, I can use only fingertip. I can use only fingertip, or sometimes I need to use all 5 fingers. For example, I want to trying to hold like this. That means all your 5 fingers and your palm will be involved in a particular task that is called holding the apple. Suppose if you want to, what to say, like just trying to pick something like a cashew nut or something from the table. So then you will be using mostly 2 fingers, where the body parts involved is only 2 fingertips. Sometimes it is not possible to complete the task. Then wrist movement will be there, especially for opening the tap, locking the tap, unlocking the tap, tightening. If you want to open your water bottle cap, so then you have to, there must be finger holding the cap, then wrist movement will be there, which will be helping us to tighten it or loosen it. It is. So then that will be, that means up to this part only will be involving in the task. So sometimes we'll be trying to move our hand, lower arm will be there along with the wrist movement. Then elbow will be the joint, which will be the point of, what to say, like a support. So then if you are trying to use the complete hand, especially trying to pick something else from the distance, or trying to pull something, trying to push something, then entire hand will be involved, then where shoulder joint will be the support. Same like we will be trying to design the human robo arm, which will be exactly similar to your hand. So when it comes to humans, already I have mentioned, human will be having bones, joints, muscles, and brain. With respect to robo, it will be having links, joints, actuators, and controls. And human body allows to walk, lift, dance, different movements. But when it comes to robo anatomy, it will be deciding how robots can interact with their world. So human body is built with bones, connected by joints, powered by muscles, whereas robo will be built by links, connected by joints, powered by actuators. And at the same time, our brain controls through nervous system, whereas robo also will be having controllers, which will be controlling through different types of sensors and softwares. And when it comes to overall, means like outline of the robo means, already I have mentioned, it is a human reflection, but which will actually work mechanically. But the structure, if you observe, it will be mostly similar to human. So with respect to the complete anatomy, if you want to understand, the robo anatomy primarily focusing on two different functions. One is structural and functional elements, two different parts, especially. What is the structural mechanism of the robo? Then what are the various functional elements of a robo that will completely means that will make the complete construction or building of a robo itself. So with respect to various elements in the robo, so first thing is you have to understand the mechanical structure. The mechanical structure means it is the complete outline or profile. What is the shape or what is the size of the robo part or robo you are trying to build. So that means the mechanical structure will be having links and joints that will be defining the overall robo shape and range of the motion. Then actuators will be trying to provide the motion. Sensor will be gathering the information from the environment. Environment means which part. For example, if the robo arm is designed to pick up the right object, like for example, the especially in quality section, if you observe the plastic segregation or waste segregation industry, they want to segregate the bottles based on the material or plastic grade. So you need to give, it may be in terms of thickness, it may be in terms of material features, or it may be in terms of size of the bottle, whatever it is. So it will sense and it will touch, means the sensors will pass the information that is after observing, after touching, this is a right bottle, it can be segregated. If the product is wrong, then it will be disposed in some other right product will be kept in right chamber, wrong product will be kept in another, means like a waste or discarded chamber itself. So especially in quality control section or segregation section, segregation of the product based on the size, shape, material, color, flavor, whatever it is. So this pick and pick is very, very important. So their sensors will be trying to gather the information from the environment. Yes, size is perfect, material is perfect, shape is perfect, color is perfect. So based on that, so that means it will be observing the environment and the message will be passed to the controller. The controller means, let's say, brain. So the controller will process the information and it will be giving command to the robo. And once the command is perfect, then it will actuate the movement. Then automatically the gripper will try to hold the object and it will be placing in the right bin itself. So this is the actual function happening in the robo, complete robo movement, how it is. So we can say that robo can be thought of as a computer which is on moving on the wheels. Yes. I don't know again whether the video will work out or not. So I don't want to take any risk for the videos. So if you observe this complete anatomy, the functioning of the complete robo it is. So this is the body or the complete structure. So this is mechanical structure of the body. So which will be having all the links, joints, everything. And these sensors will be trying to sense the information from the environment and it will be passing on to the mind. So mind will be taking the decision whether action can be started or not. So once the action, mind has given a signal that is, it is the right environment, right product, right object, yes, the movement can be taken place. Then immediately it will start acting it. That is what actuators will be trying to release the movement so that the robo will move and start working on this. So this is the sense plan act framework structure of a robo. It is how the sensors will be taken place and how the sensed information will be processed and how the processed information will be sending to the controller to pass, to release or to give permission whether the movement can be taken place or not. So with respect to this, again, so here again, it is connected with physical construction of body, arm and wrist. When it comes to robo structure, the lowest part, the bottommost part of the robo, especially if you observe the anatomy, it is called base. So the base is mostly fixed to the floor if it is working in one particular place and having what to say, like orientation or reach all 360 degrees surrounding. Some of the robots or robo arms, anything it is, if it is placed in the continuous assembly line or production line, so the robo duty is just to place the part at a particular point of time so that it will be attached or assembled to another component. So that means the base will be fixed to the floor on the particular place. Then the robo arm will be moving surrounding all 360 degrees, depends on the position of the conveyor or depends on the position of the machine to pick the object from the tray and place the object on the machine or place the object on the conveyor so that the part will be taken to next stage of assembly process itself. So the bottommost part is base, which will be either fixed. If it is a mobile robots means it will not be fixed. If the robo is located in one particular position for a particular task continuously, so then the base will be attached or fixed to the floor. That is the bottommost part. Then the entire body of the robo is attached to this particular base. Then the entire arm assembly is attached to the body itself. So then at the end of the arm assembly, we'll be having a wrist. So that is what same thing it is. Shoulder, you can consider shoulder as a base point. The complete body is complete arm, both upper arm and lower arm, including elbow joint. So then it will be connected to the shoulder. It will be connected to the shoulder. Then at the end of the wrist, we'll be having the end effectors. End effectors are actually not part of the robo, which will be helping us to grip or to hold the object, to place the object. So to do whatever is the action. Suppose if the robo is used in welding application, the end effector is a torch, welding torch, which will be helping us to do welding. Suppose if the robo is used in painting applications, the end effector will be holding the spray gun, then it will be trying to spray the things. So only up to wrist will be considered as a robo part. This end effector can be of any shape and size. So that is depends on the application, whatever is the tool you are going to use for a particular application. If it is for welding application, welding torch. For painting application, painting. If it is for controlling, if it is kind of segregation, then it will be like a small fingertip only. Again, it will be like a human grip only. It is. So end effector is not actually part, but which is a supporting device to hold, to make the action complete with support from the entire robo arm itself. So that is why, and this wrist will be oriented in multiple ways. Again, depends on the application. So you can see here, this is the simple robo arm. We can check it. So this is the base which I have mentioned. Base will be fixed to the ground. So sometimes this base, it is also called as the first axis or first base or support. And this base will be connected to joint 1. So the joint 1 and base is connected by a link this is called link 0. So link 0 means it is supported. This is the link which is connected another part with the base support itself. So that's why link 0. Then this is the joint 1. So according to our human hand, if you observe, shoulder is the base, elbow is the joint 1, and the upper arm is called link 0. Then from elbow to wrist. So if you observe here, so this is the elbow, this is wrist if you take it. Then this is called link 1. This is the second joint. So this is called lower arm. This is our lower arm. Then this is the wrist point from wrist. So whatever is your palm, entire finger structure, everything, that is called end effectors. So this is called end of the arm. This is called end of the arm. So based on this, we'll be trying to decide how you need. So now with respect to this particular structure, you can see here, again, same thing, it is in a different ways. It is the base. This is the waist direction. I'll show you how the movement for this particular joint, how the movement for this particular joint, how the movement for this particular joint, how it will be holding. So the complete base, this will be called as a waist according to human term. There will be motor connected. So power cable will be there, which will be sourcing the power for movement. And this is the lower arm. Again, it is also called as a link. This is the elbow. This is called as a joint. Upper arm. According to this particular structure, it will be lower arm. This is upper arm. So then this is the wrist joint. So then this will be called the finger complete structure. It is called end effectors or gripping mounting, gripper or clamping or end effector, whatever it is. So this is the way how we'll be trying to design the robo arm. So you can see here again, different axes. The first axis of the robo will be decided by base. Then link one or the joint one, that link one or joint one, it will be second axis. Then third axis will be according to the third link. Then there will be wrist. Again, if you want to connect a multiple, what to say, like a end gripper in a different designs, again it will be having sixth axis and fifth axis. So you can see here, this base will be like a human, what to say, like a hip movement, human hip movement, how we can turn to move our hip. So that is the thing. That means if you observe the robo arm, it will be trying to revolve around. So that is why here, if you observe here, the movement is revolving or rotational. And here, if you observe the hand, the arm, we can try to go with forward and backward. So then we can try to even have the rotation in the wrist movement. You can try to do even the wrist. Then the wrist can be done up and down, up and down. So then it will be even try to, for example, if you want to tighten knob, the fingers will be helping us to swivel it. Again, that movement is there. We can try to, means the movement will be again revolving both clockwise and anti-clockwise for locking and unlocking itself. So you can see this, what are the different movements, what type of movement, of course, that we'll be trying to discuss in the next slide itself. So different axes with respect to the structure of the robo from bottom to top. So you can see here, we can compare what are the different types of movements, especially in the robo in comparison with human, So especially first axis, that is base. So it is a waist movement or hip movement. Waist movement, how the human can try to turn. So it will be like a swing, means like a, like a revolving direction. So you can try to move left or right, front, you can try to lean the front, but you cannot completely bend back. So that is the movement. Then second axis, it is representing the shoulder. So how the shoulder can be done. So you can try to lift your shoulder, you can try to make it perpendicular, and you can try to make it down it is. Then again, third axis is elbow. From elbow, how we can try to do all the movements, that we can try to check it. Then wrist. So wrist, already I have mentioned, it can be rotated. So then again, wrist bending, that is fifth axis. It can be done front, back, but again, it cannot be completely back again. So wrist you can make it front, you can just revolving it is. Then fingertips, you can even rotate like this, and you can even hold like this. So like this, with respect in comparison with human body part, how the robo links and how the robo joints can be created, and how the movement, what type of movement can be generated for a particular part as per the axis and as per the links and joints in the robo itself. It is mostly similar to human movements only. This. When it comes to main components of a robo, the first one is power supply. This is the energy source. This is the energy source which will be driving the complete robo system itself. So energy source, of course, there are different varieties. So electrical energy. So sometimes you can think of multiple sources it is, but this is the energy source. Then software and programming is very, very important, because the controllers, sensors, the complete everything, actuators, everything, it will be depending on this software programming only. So the control system, it is like a kind of brain for the robo, which will be processing the input and trying to execute the commands. So trying to check that output will be perfect. Then the motors and actuators, it is a kind of muscle or energy boosters, which will be helping us to make the movement, helping to the robo to make a movement in the particular part. Then end effectors, already I have mentioned, it is a robo hand. So whatever is the tool, based on that, end effector will be changed. Then mechanical structure, already mentioned, it is a body frame, which will be having links and joints to decide the complete structure of the robo itself. So this is the complete unified system of a robo, mechanical structure, physical foundation for the robo. This is the first thing which you need to understand. So this mechanical structure will decide how many links are there, how many joints are there, what will be the size of the robo, everything. So to make this system for action, to make it act or to make it function, then you need to have control system. So the control system is a brain which will process the inputs. But to make the control system again functioning, you need to have energy source. So that is what power supply. So the energy means it will be driving the entire system. Then whether the work is perfect or not, all the actions, the functions are performing as per the command or not, that will be decided by software program. So which will be developing a logic, how to do, how to pick, how to place, what to do, what not to do, everything. Then motors and actuators are energy boosters like a muscle. So these muscles will be enabling the movement, and especially for physical action. So then end effectors, which is a tool which will be interacting with the environment actually. So, so for example, we have very big body. If you try to touch the hot object, when you are trying to touch the hot object by mistake, so automatically entire body will react. But your point of contact to the particular environment is your fingertip, your fine fingertip. Once the moment you touch the finger, means your finger touches the hot object, automatically entire body means like one small jerk. So something happened. It is so that means you just imagine the speed of human brain function, how fast it has taken the signal, how fast it has reacted the body, so that in a fraction of second time we'll be trying to take our finger back. So that much speed functioning we are trying to incorporate in a machine which is developed by a human. So and these machines are now overtaking the human, and fast means like their work will be faster, even 10 times, 20 times, 100 times faster than human itself now. So this end effector is the tool which will be actually interacting with the environment, where we will be working with which tool will be working, what exactly we are trying to do it. So then sensors are the devices which will add intelligence to the particular machine. So that is what which will be providing whether the environment is perfect, whether the object is perfect. It will be giving feedback to the controller, then automatically command will be executed so that the movement will be either proceeding or controlling itself. So the important part when it comes to robo, so the important part is link. Link is a bone in the human body. In robo, it will be called as a link. So this is the very, very rigid part which will be providing the structure to the robo, and which will be which will be connected. Means multiple. Of course, if there is only link, it cannot be working. This link must be connected to some other link. Then structure will be formed. If we have too many bones in our hand, so we cannot make any structure. If the one bone is connected to another bone, then we can try to make some structure, and this structure we can try to create some movement to do some function itself. So that is why these are the rigid parts. But this rigid part will be in function if it is joined or connected to some other link itself. So that is why what is the main function of this robo link means. So they form the skeleton of the robo, and which will be using for transmitting the motions, movement, and forces to different links and all. So it is also called as arm, because you can see here, this is the base. This base is called as link 0. This base is connected to another joint. This joint is connected to another joint. This is link 1. Then this link 1 is connected. Here, if you observe here, this is another joint. So this particular portion is called second link. Then this particular joint is connected to another joint. So this is called third link. So then again, it is connected to some other joint. But here, if you consider it as a joint, it is a joint, or the link itself is connected like this. The link itself is connected like this without joint, which is having frame. So the frame itself is here L frame, so which is connected here. So if there is a joint, it is a joint. Again, it will be two links. If there is no joint, it will be only one link. Now you can see here how the end effector will be. It will be in multiple shapes and sizes. Here, if you want to observe how many number of links are required to construct a robo, so that is depends on like a number of joints you are expecting. So now movements, and what is the functioning you are expecting to do by the robo itself. So the number of links will be from 0 to n minus 1, where n is number of joints. If there are 100 joints, the links will be from 0 to 99. The links will be from 0 to 99. For example, you take our elbow and wrist. Elbow and wrist is connected with one arm. This is called our lower arm. So, but wrist is one joint, elbow is one joint. That means two joints will be connected by one link. Then this joint I can extend and I can connect to some other joint. So that means number of links will be always equal to minus 1 of number of joints. That means number of joints minus 1. So that is the first principle which we need to follow. So you have to decide how many joints are required. So based on that, we can calculate how many links are going to be introduced into the particular robo structure itself. Because this link will be deciding the overall framework of the particular robo. So then if you observe here, this is one of the joint. This is one of the joint which is connected by a link. So here, this is the joint axis. It is called axis I. Here it is axis I minus 1. These two are connected by link I-1. And if you observe here, there is a line which is drawn perpendicular to axis I-1 and connected to axis I. So this line is called common normal. There is a term called common normal. This common normal means it is the shortest distance which will connect the two axes, which will connect two different axes. That means two different joints. So two different joints. So then if you observe the angle between this another axis and this common normal, if you observe this, the angle is here alpha I-1. This alpha I-1 represent how much twist I can give to the particular joint. For example, wrist joint, how much twist I can give to the robo, so that what will be the degrees of freedom to the particular joint and how many directions the joint can move, so that accordingly we can try to manipulate the part to pick to do the function itself. So that is called twist angle. It is twist angle. So this is called common normal, which is the shortest distance between two joints. So this will be deciding even the length of the link required. So you can see here multiple base, link 0, joint 1, how it will be connected. So what is the main function of the link? What exactly it will do means, it will be providing the structure and shape, maintaining the spacing and orientation between the joints. So it depends on the length of the link, how much gap should be made. Just imagine your right hand length and left hand length, if it is not equal. If it is not equal, is it possible to do the task similarly or as effectively as possible in the similar direction? So just imagine what is the length of the right hand, what is the length of the left hand. So if there is a difference in the length of both the hands, just imagine how our functions, how our activities will be different. So here, these links will be deciding what is the orientation, that is how much space it will cover, and what will be the spacing between the joints, that it will be deciding, and it will be also determining what is the reach. That is, reach means, for example, if I'm trying to place a robo here, what is the size of the conveyor belt? To what extent it can pick up the, for example, if the conveyor is very, like wider, and if the, like a bulk amount of products are passing over that, and during movement, the robot need to pick up which is the defective component by sensing it. So then how, to what extent the arm can move. So that is called reach. Then what is the support required, especially in terms of loads and to transmit the force. So if you observe here, this is the complete work envelope. So this circle, outer circle, if you observe, this is called complete work envelope. That means up to this much space, the robo arm can work. Again, here for you, as an individual, if you want to design your work table, so in your table, if you want to decide wherever you will be sitting in the office daily, if you are not properly organizing all the things, each and every time we'll be trying to search, where is the pencil, where is the eraser, where is the book, every time itself. So how to design your work table so that you will be spending time very effectively to avoid searching of the things daily. So what should be the size without having even a movement or single stretch, even simple stretch, you can try to pick the objects. So how it will be deciding means, take your elbow as a center, your complete lower arm till fingertip is the radius, just to draw the semicircle. Just to draw the semicircle, that will decide your minimum reach or minimum work area, or minimum workspace. Just to draw the semicircle in front of you, that will decide minimum reach. That means if you try to place anything within this minimum space, you no need to bend again and again to pick or to use some of the objects. That is your minimum reach. So this is the space usually people will suggest, industrial engineers will suggest, try to locate the objects which are very frequently required, which you will be using continuously in the minimum space. Then maximum space means your shoulder will be the center. Your complete hand length will be the radius. Just to draw the space, semicircle in front of you. This particular area will be deciding your maximum reach. In the maximum reach, again here also, you no need to bend either left or right or front, whatever it is. But still we are able to pick up by stretching the entire hand, and we can try to pick the object itself. That is maximum space. Yes, this is also fine. You no need to make any movement to pick our objects, and try to arrange the things which are important and which are required without any movement. If you need the object, then you can, especially in the hospitals, in the operation theater, when the doctor trying to do surgery, what are the tools they need, what are the surgical instruments that they need, whichever instrument they'll be using continuously or very frequently, that must be located in minimum reach area, and whichever will be used occasionally, but it is important, maybe or may not be used, but still it is required. So they'll be trying to keep it in maximum reach space. If the space is not accommodating all the surgical instruments, then there will be supporting staff. So they will be holding the things who will be supporting to the doctor during surgeries itself. This is the way how we'll be trying to design the workspace. Same design concepts we'll be trying to use even to design your robo. So what is the minimum reach? What is the maximum reach? To what extent it will be going? So this will be decided by links. Already I have mentioned provide structure and shape. So which will be creating the skeleton, overall geometry, shape, and there are different types of orientations which will be deciding the links connection that we'll discuss in future slides. And it will be helping first maintaining the spacing, orientation between the joints. Just now I have explained what exactly it is. So then it will be helping us to determine the reach of the object. So to what extent the robo arm can pick up the object. For example, you take your remote in that TV remote in your house. So from which place, to what extent you can use the remote to operate your TV. So that is called reach distance. That means up to the particular distance, the sensor will work. If the reach space means is high, automatically sensing capability will be automatically less. So that we need to decide how big links we need to use. If the link size is larger, automatically space will be high. That is reach will be high, but at the same time, sensing capability will be little less. Then at the same time, these links will be helping us to support the loads, especially for forces, torque, bending action, and different types of loadings. And we need to think about what is the material is suitable for links, which must be as much strength as possible. It must have proper stiffness and vibration resistance, and it should be strong, rigid, since it is a rigid body, and what is like a basic support for the entire structure of the robot. And you need to think about the material which will be highly durable. So these are the points which we need to remember, especially when you are trying to decide the links. And what exactly means, especially in the robo, what are the various types of the links we'll be observing? Basically 3 types. So first one is base link. Already I have mentioned. This is the base, which will be the bottommost part, which will be what is like attached to the ground or floor. So which will be, this is the it can be considered as a chassis base support in the how the chassis will be in the car. Same like in the robo, this base will be the chassis, will be acting as a chassis. This is the support. Over this entire robo will be building. So that is called base link, which will be providing stability, load distribution, and trying to referencing all the coordinates for different kinematic moments. Then another important thing is primary links. So primary link means they are the main members, especially in the robo structure, especially with respect to this complete hand. If you take it, shoulder can be considered as a base, upper arm and lower arm, these two can be considered as a primary links. So these two primary links connected by elbow. So it is which will be deciding the overall workspace till what extent the robot can place the object and can pick up the object, can do the service. Then at the same time, it will be considered means how many degrees of freedom. So how many directions the robot can move. So that will be decided by these primary links. Then third one is end effector link. That is what? Wrist. So the wrist means it is used for gripping, welding, screwdrivers if you want to tighten it anything, if you want to do painting. That means whatever is the tool you are going to use, this gripper will be holding the tool. But this particular link must be very, very careful, must be designed very carefully, because this is the part which will be in connect with the environment, this is the part which will be actually involving in the work. So it must be precision, easy tool attachment, and it must handle the play load, whatever is the weight of the particular. For example, if you are trying to attach the welding gun or welding torch, so then what is the weight of the welding torch? What is the shape of the welding torch? So this end effector must try to hold it, must try to hold the load, must try to properly grip the shape of the particular one, whatever is the material, whatever is the texture, each and everything we need to consider to design this particular gripper itself. So when it comes to parameters, design parameters, if you want to design a link, in the robo. So first thing you have to check about the link length. So it is a distance between two joints, frankly speaking. So that means physical length. So then you have to think about the link twist, how many directions it will be, it can be twisted. So already I have shown in the previous example. So in how many directions, what is the maximum twist angle, so that it can rotate, or it will be having free degree of movement in multiple directions. Then link offset is the distance between reference frame where exactly we're trying to measure. So then how much sliding it can be done along the joint with respect to the axis. So then joint angle. So joint angle, again, see here. For example, if we take elbow joint, shoulder joint or elbow joint. So here, with respect to this lower arm, with respect to the joint, I can make 90 degrees, I can make 60 degrees, and even perfect 0 degrees, whatever it is, up to 90 degrees. But when it comes to any acute angle or obtuse angle with respect to horizontal plane, it will be very difficult because the joint will not allow me. So that is why we have to check it. What type of movements will be allowed by the particular joint? Either it is rotational movement or transitional movement. If it is a rotational movement, again, what is the angle, twist angle? We need to check. That is called angle. If it is a transitional, what is the reach? How much front, how much back? So this is very important, especially when you try to design the joint angle. So the second important part, especially in the robo, is robo joints. So link is the rigid part, which will not do any work if it is alone. If two links are connected through joints, then it will try to act. So same thing. If you are holding multiple bones in the human body, so 206 bones will be there. So these 206 bones, if it is not connected each other, the human skeleton will not form. Over the skeleton, muscle will not form. Over the muscle, movement will not be taken place. The movement will not be controlled by human brain. So that is why these links must be connected each other. Then structure will be formed. Once structure is ready, then we can try to enable movement in the particular structure. Then the particular machine can start functioning for whatever purpose you are trying to design. So joint is the important part, especially in the robo structure, which will be essential component, especially for manipulating or for usage, especially whatever is the thing. So if two links are connected, wherever these two links are connected, that is called the joint itself. So this joint will be deciding in which direction, in how many directions, what is the space, everything. So based on this particular joint. If this joint is not proper, automatically the entire link cannot be properly functioning itself. So you have to check it. The number of joints, it will be from 1 to n, and number of links will be 1 less than number of joints itself. Again, there are different varieties of the joints. So first variety is prismatic joint. If you observe, all of you are familiar with CNC machines. In the CNC machine, the table movement, it is a prismatic joint. So that means the table can move x-axis, y-axis, z-axis. You can try to adjust in multiple ways. So that means only transitional movement. There is no any rotary movement. That means just a linear movement itself. So the joint, if it is allowing only linear movement for the link, that means just front or back, or left or right, that's all, no rotational movement. If it is given, that is called prismatic joint. Or the axis along through this particular joints is called prismatic axis. It will permit only linear movements, no rotational movements. That is one type of joint. Then revolute joints, especially you can observe the gates, doors in the house. So it is a kind of hinge joint, which will be allowing for rotation along the single axis. So so here it is a kind of hinge joint. The door can move front, back along the joint, and sometimes the door can be completely 360 degrees rotation also. It is, you can take it front and you can take it, mostly it is what is like hinging kind of thing. So if you observe, this is one link, this is another link. So this link can rotate along this particular axis. So rotation is allowed according to in the direction of the arrow itself. This is a revolute joint. Then helical joint is exactly replicating the screw movement. So if you are trying to fix the screw in the wall or to the machine part, anything, how will be trying to fix it? It is completely rotational. So and along a particular axis, we'll be trying to rotate. So the rotational movement will be enabling the screw to move inside and trying to fit it. So but there will be axis. The movement will be along the particular axis, but the screw will be rotational. The screw will be rotational and the movement will be taken place transitional along this particular axis itself. This is called helical joint. Then cylindrical joints both, it is a similar to revolt joint, but at the same time, there will be even series with prismatic joint, both the combination it is. So rotation will be there, again linear will be there. So which will rotate and again move front and back itself. So that is called cylindrical joints. Again, depends on the application, we need to create the joint. Then spherical joints means it is like a ball and socket. So 3 revolutions, will be trying to inserting a point, which is called pivot, and with rotation, we'll be trying to make it. So that is spherical joint. Then universal joint means trying to make 2 hinges joining this. So this is 1 hinge, this is another hinge, we'll be trying to make it. So then 2 degrees of rotational freedom about this intersecting joint. So that is called universal joint. If you observe here, what are the varieties of the joints, how it will be. This is the base. Here, they have mentioned it is revolute joint. That means they will be having rotational moment from this joint to this joint. Here, these two links can have revolute joint. And when it comes to these 2 joints, it is a prismatic joint. That means this can slide front and back and it can fit. So then this is the end effector. So it depends on the requirement here. Again, these are wrist joint, this joint 5, joint 6, joint 7. Wrist joint means it will rotate, it will move up and down, front and back. So then here elbow joint again. So then with respect to shoulder joint, again, it will move up here. You can see here. This is linear movement up and down. So here this elbow joint, here it is represented here. Then shoulder joint, you can lift the shoulder, you can make it right side and left side, how it is. So if sometimes the robo will be connected with all types of the joints also. So you can hear again how the robo arm will be connected if you want to hold the job, especially very precise micro level jobs and that. So base joint, shoulder joint, how it will be connected, lower link, elbow joint, again upper joint, upper link, then wrist joint, then wrist is connected to end. So if you want to make these joints to move, how many directions the joint? So first one is link. Link is 2 links are connected, so joint is formed. Now I want to make these 2 links to do some action. So to make the action in the particular robo, what we need to understand before giving some movement means that we need to check what is degrees of freedom. So degrees of freedom is deciding or defining motion capabilities of a particular system. So it is depending on total number of independent movements a joint can perform. So same thing, if you take our elbow, we can try to bend the hand like this and you can try to lift it. And you can even try to do like this and you can try to, but backside is very difficult. But if someone asks you to, what is like a bend your hand at elbow point to the backward, our hand will break. Means the joint will, this particular elbow will break, that's all. So that's why we have to check it. What is the degrees of freedom? How many directions the particular joint will allow the link to move? That is called degrees of freedom. Here, most of the manipulators, they'll be containing both rotational movements and linear movements. So all together will be deciding degrees of freedom itself. So if you want to decide number of independently driven joints, what will be the degrees of freedom means? If degrees of freedom is increasing, computational complexity will be very high. If you want to design, of course, now we are talking only joints in oral, but when it comes to actual calculation to make kinematics, that is movement in the particular robo, so you need to consider each and every link, each and every joint, what is the degrees of freedom, so what is the reach, what is the orientation, each and everything we need to check it. If degrees of freedom is high, the computational complexity also will be very, very high, and the cost also will be high, but highly flexible. That is one important thing. And in general, if you observe, we'll be having 6 degrees of freedom with respect to 3 different axes. So with respect to x-axis, linear movement and rotational movement. With respect to y-axis, again, linear movement, rotational movement. With respect to z-axis, again, linear movement, rotational movement. So z-axis up and down, clockwise and anti-clockwise rotation. X-axis, again, move forward, backward, again, rotational. Similarly, y-axis. So means both transitional and or linear movement and rotational movement. So why degrees of freedom is important, especially in developing the structure of the robot means already I have mentioned. So this degrees of freedom will be independent for each and every link, and it will be deciding what is the reach point, and it will be deciding how many directions we can provide the workspace. For example, elbow, if you take it, try to take anything which is located from the front side. I cannot take, of course, I can try to take like this. But if I want to bend and do something, it will be very difficult, which will not be deciding the work. So that is why we have to check it. This degrees of freedom will be deciding what exactly the reach space or workspace and what is the orientation, how the joints are located. So based on that, we can design the workspace for the robo so that the activities will be functioning within the particular district. And this degrees of freedom will be defining workspace volume. Already I have mentioned what will be the shape of the work shape. It can be spherical, it can be cylindrical, it can be rectangular, depends on the joints. And it will be helping us to improve what are required. And means like kinematics means how many movements, whether it can be forward or backward, or it will be completely, sometimes it will be completely dynamic also. So this will be deciding what essential, means what are the requirements or essentials to introduce kinematics in the particular robot. So if you observe a human hand or human arm, sorry, so human arm, so we have totally 7 degrees of freedom. You can observe 3 rotations are in shoulder, 3 rotations. You can lift up, you can lift down, make it down, and you can make it a linear movement like this. So that is 3 rotationals, or with respect to the shoulder, you can make it like this, and 1 rotation at the elbow, so and 3 rotations at the wrist. So totally 7 degrees of freedom, especially for human arm. Same like you can design and you can get same degrees of freedom. And if you observe here, with respect to degrees of freedom, we'll be trying to call it in different terminologies. One is pitch. Pitch represent bend up or down. So that is called pitch. So what is the pitch of a wrist? So how much distance it can bend down and bend up. So now if I say here, this is my wrist, I can bend. So if I'm trying to make like this till here, so from this point to till upper position till up, this entire space I can consider as a reach space with respect to pitch. So the pitch represents bend up and down movement. Yeah, left and right movement. So how much direction, how much area I can cover for left and right. So only with respect to, again, wrist I am telling it is. Then rolling, swiveling action. So when I'm trying to lock or unlocking the bolt or tap or water bottle cap, whatever it is. So how much swiveling action the wrist can do, that is called rolling action. So all 3 movements can be introduced at a particular joint, but again depends on the links, depends on the requirement, and depends on the force, depends on the energy source or power source you are trying to provide it. So here this particular table represent what is the degrees of freedom for each and every part, each and every joint in our particular, in our body. It is, you can check it here, how many directions each and every joint in the human body can rotate, can move, means will have free movement in multiple directions. So same structure if you observe, so this can be adopted even for robo. It is the full. Then when it comes to configurations, as we have discussed about links, we have discussed about the joints. Now links and joints are created, but how we are going to connect these links and what type of movements can be introduced with respect to the joint. When you try to connect at a particular joint, what type of movements can be created. So in how many ways the orientation can be, configuration can be done in a particular robot with respect to links and joints. That means how the links and joints are going to be arranged. So that is what here robot configuration. There are multiple varieties of configurations. Again, depends on the requirements. We can try to attach these links at different joints with a different orientation or configuration. So which will be deciding the complete movements, degrees of freedom itself. So again, if you observe here, the first one is Cartesian configuration. Cartesian configuration means here only linear movements, no rotary movement. Like already I have mentioned, CNC machines. CNC machines, especially the bed of the CNC machine, which will move only in the linear direction, front and back, right and left, up and down. That's all, bed. So this is what linear movement. So this is called, if all the links are attached, which will permit only for linear movement with respect to multiple axes, that is called Cartesian configuration. That is called Cartesian configuration. Then another kind of configuration is cylindrical configuration. In cylindrical configuration, it will provide, the joint can provide one rotary movement and two linear movement. You can observe here, this is one of the link, this is one of the link, both are connected here. This link can rotate, can do swiveling action, rotation, rotary movement, and at the same time, this particular one can go even move up and down, and this particular link can go even forward and backward it is. So this is called cylindrical configuration, where rotary movement and linear movements both are together. Then spherical configuration is, so it is completely like a what to say, like a hip movement in the human body. So the base where we, this particular, if you observe this particular link, which will be having complete what to say, rotary movement, it will, means it can have rotation, especially one example is like in the what to say, like exhibitions and the giant wheel. So it will be having complete 360 degrees wherever it is rotated. So it means it will be having complete 360 degree rotation with respect to the particular joint. And similarly, the same giant wheel, once it reaches top, it will rotate 360 degrees. Similarly, the entire structure will be having linear movement. It will come along the particular link, along the particular, it can slide down again, where all the means like the customers can get down from the giant wheel itself. So it is like both the rotary movement, linear movement, but here in spherical configuration, many rotary movements, less number of linear movements. And another important thing is articulated configuration or revolute configuration. Here only rotary movements, no linear movement. Only rotary movements, no linear movement, especially like a human arm. Especially like a human arm will be trying to rotate. So of course, human arm, so I can just bend and make it, but I cannot extend my hand. I cannot extend my hand. So only depends on my arm length. I can try to extend up to that, but beyond that, I cannot extend. That means there is no linear extension for my arm, but I can rotate multiple degrees. So that means here only what to say, like a rotational movements. So that is called articulated configuration or revolute configuration. Then very simple kind of configuration is delta configuration or parallel configuration. So here all the arms are connected to a single platform, very light in weight, but very extremely fast. And this is very common, especially in sorting chocolates and biscuits with respect to size. With respect to size, especially packing under, once the required packing is done, it will pack, it will segregate, and it will send out. If either less or extra, again it will. Similarly, the shape of the chocolate, shape of the biscuit, color of the biscuit, color segregation, especially in food and the electronic industries. So this data configuration is very, very common. Then another one is SCARA robot. It is also very, very common, especially for industries. So selective compliance assembly arm, it is frankly speaking. So which will be having both the linear movement and rotary movement. Again, this is also related to kind of cylindrical or what to say, like a spherical one. So which will provide one linear movement and two rotary movements. So providing a cylindrical kind of work environment. So means like if you want to rotate 360 degrees or in a circular environment or cylindrical environment. So this particular robo is what to say, like highly suitable. So these are the common configurations usually people will follow. Only linear, less linear, more linear, one cylindrical, more rotational, less linear. And SCARA robot, very simple structure, articulated only rotational movement, and humanoid, complete human structure itself. So what exactly the kinematics means? Of course, now we created complete structure, how many links, how many joints, how these links and joints are arranged. So done. Now we need to add movement to the particular joint and to the particular link so that the particular, what to say, like a robo, whatever we have developed, it will start functioning. So how to add movement means that is called kinematics. So how much force is required, how much energy source is required, what is the load bearing capacity, what is the position, what is the velocity, is there any kind of acceleration. All these things can be what to say, like will be handled by kinematics. That is called robokinematics it is. So with respect to this, again, there are different types of robokinematics we'll be trying to discuss. So this itself is a big chapter where you can do what to say like you can study a lot, and it is completely related to calculations. Different types of mathematics will be involved to calculate overall kinematic parameters and all. So how actually means how efficient the particular robo or the manipulator to do the particular task itself. So when it comes to forward kinematics, it will be computing end effector position and also orientation, especially when joint parameters are known. So that means what exactly the end effector position, either it is fingertip or all the fingers, or what is the shape of that, where exactly it will be starting, and how the moment of the end effector, all these things, that is called forward kinematics. That means first we'll be giving input as a joint angles, then output will be end effector pose. For example, if you want to do welding, then you have to give input that what is the joint position, where exactly. So now my welding torch must be holding like this. So with respect to the plate, it must be in this particular direction, and how much, what is the like length of the welding plate, how much distance the welding must be done, and what is the beginning point, what is the ending point, and what should be the angle position, means in which position the robo should hold the welded torch. So that will be decided by kinematics. So you need here, with respect to forward kinematics, your input will be your joint angle, in which direction it will support that, and output will be end effector position. That means it may be welding touch. So for example, if you are using for spray painting, then so how the spray gun must be holding, so then in how many directions, and what should be the degrees of freedom, so that the robo arm can spray in all the directions, which will cover entire space itself. So these things we need to check it, what exactly we'll be trying to do in forward kinematics means, it will be calculating the positioning and orientation of the round effector. And how it will be actually working means, it uses robo geometric structure, that is called, what is the structure, how many links, how many joints, what is the degrees of freedom for a particular joint, which will be deciding actual end effector location. And analogy, if you try to take it, angle of your shoulder, angle of your shoulder, angle of your elbow and wrist, which will be deciding whether your hand is pointing in the right position or not. Then another kind of kinematics is inverse kinematics. So inverse kinematics means, again here also of course joint parameters is the key factor, but input is decide pose. What we are trying to do is, we are trying what exactly you are expecting, where exactly the robo should touch, what exactly they need to do, that we are trying to give it as input. According to the required position, the joint will be adjusted, that is called output. So it is called inverse kinematics. In forward kinematics, first according to the joint, we'll be trying to decide how to hold the job. But here, first we'll be trying to give for this particular one, what kind of joint is required. So that is called inverse kinematics. Then differential kinematics means here both related to joint and also end effector velocities. Here, Jacobian matrix is coming into the picture. We'll be trying to calculate all the kinematics using this Jacobian matrix, and especially for smooth motion, real-time control, avoiding all the signalarities. So not to means like by finding the accurate space, accurate orientation, accurate reach, accurate workspace, everything. So here both will be considered. So this is what I just want to thank you. I mean, so like I just want to convey in this particular session. Hope I have covered at least minimum basics related to robo anatomy, and what are the parts, what will be the structure. But this kinematics, if I try to extend, I can explain one big problem with respect to taking a simple structure of the robo, and based on each link, each joint, what parameters we need to take. But it will take another, what to say, like a 2-3 hours session to explain completely. That's why I have just given inputs. So with this, I just want to stop. Hope I have given some information to you. If you have any queries, I may help you to answer. Thank you.
Dear participants, any questions? Please feel to ask. I requested participants, please unmute your mic and ask the question. One participant asked a question.
Yes, sir.
Degree of freedom is required to find at each joint, ma'am, or for
Yes, sir.
whole robot structure, ma'am?
No. It is with respect to joint.
It's
It
a
is with
question from
respect to.
Shobana.
Yes. It is with respect to joint. Degrees of freedom will be deciding with respect to joint.
Another question is from Vijay Singh. Is any software to design a robot?
Design means like what to say, like a complete structure you are asking?
Sir, Vijay Singh, sir, can you unmute yourself and ask the question to directly, ma'am, sir?
Madam, I've got a question, madam. I'm R.S. Kiran from FDP Engineering College, Visakhapatnam.
Yes, sir.
Madam, which are going to be superior in the future? Is that robots or cobots, madam?
Actually depends on the application, sir. Especially related to warehousing and all.
We are looking out for a warfare wherein
Yes,
the human can be replaced by cobots, not
yes.
robots.
That is what, especially in warehouse and all, cobots are very famous.
Very famous, yes.
Yes. Cobots are means like what to say, like if things are arranged automatically, if they are properly labeled, then cobots will be more than sufficient.
And which is costly to manufacture for India? Is that robots or cobots? Fabrication aspect.
Means like intelligence wise, we need to have cobots. Again, decision making again depends on the situation. We need to check it, sir. It is like how much intelligence, what is the type of the situation. Again, means like how vibrant it is. What is the means like for example, especially related to environment, mining situation and all. So we need to predict it. What will be the environment? Okay, how it should react. And even in the machine failure, how the robot should react. So these things are important.
So if we say that tomorrow it's going to be floorless factories, so would that be correct, madam?
It's not like floorless factory in the sense, of course, floor is required, human is required because we are only controlling the program. We are only controlling the program. The only thing is human, what is like human is replaced by robo, but robo is controlled by human. So we need to update our skills to control whatever we have invented.
Designed, yes.
Yes.
Thank you.
Actually, there is no any kind, means it is like a myth only. If there is a completely automation, there will be what to say, like a manpower loss in the factory, a job loss in the factory, and it's not like that. Because since we have invented, we need to adapt ourselves how to control that, how to extend.
Yes, madam.
Yes.
Thanks, madam. It was really wonderful and insightful.
Thank you, sir. Thank you.
Dear participants, any doubts, any questions can ask. Please feel free to ask the ma'am.
Hello.
Yes.
Yes, ma'am. A robot may be designed for a 5 kg or a 50 kg. Depends upon the weight shifting.
Yes.
So I am asking about the depends upon that weight is changing. So structure will be changed.
Yes.
So is any software is there where we put the weight or directions or all the things? Is any so able to design that robot?
It is completely depends on kinematics. Means what exactly the load you want to give. Okay,
Yes.
what is the structure you are trying to decide? Okay, so then what is the motion or movement you are expecting from the particular joint? Okay, then at the same.
But at the same time, we I think can be designed as such a type of software which is all the things we will place and some output may be there.
Yes. Sir, I'm not very sure about the softwares because I'm working towards Industry 4.0, not completely related to robots. So I'm trying to work towards sustainable manufacturing than smart manufacturing. So that is main area. But since I'm trying to focus on Industry 4.0, I started learning about robots and what exactly the construction, everything. But I'm not very sure about the robots. But if you want, I can try to find and convey.
Okay, thank you, ma'am.
Thank you, sir.
Dear Vijay Singh, sir, there is some softwares to design the robot payloads and all those things. That Saturday session, we will explore about the software, what softwares we have for designing the robot and payloads, kinematics, all those things, sir.
Okay, thank you, sir.
Sir, Vamsi sir.
Gurumesh sir.
Sir.
Yes, sir.
If there
Sir, thank you. Yeah. So with your permission, madam and other
Yes.
participants, can I conclude the session? Is there any other yet to ask the questions? So good evening, everyone. As we have discussed a long time, 1.5 hours, and we discussed about the various topics like robot anatomy, kinematic links, degrees of freedom, and human compared with human in industry 4.0, 5.0, and functional elements, and as we degrees of freedom, configurations, for kinematics, inverse kinematics, kinematics, like this, discuss entire session and has given a very doubt clarification. Thank you, madam. On behalf of our College of Engineering and all participants from the ATAL, as you have spent valuable time with us and you enlighten us with any basic of the robot, and I would thank all of everyone again for giving us a sharing valuable information.
Thank you, sir, for your opportunity.
Further events also. Yes, ma'am. Thank you, ma'am.
So thank you for your opportunity. I try to share something based on my knowledge. Of course.
Sir, thank you.
Yeah. Yes, sir.
Yes. Thanks.
Thank you. Thank you.
Ma'am, thank you very much, ma'am.
Thank you, sir. Thank you.
Ma'am, participants asking your presentation notes. If there any...
I'll share it. I'll share it. I'll share.
Then we will share to participants.
Yes, 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 yes.
Thank you very much, ma'am.
Thank you, sir. Thank you, sir.
You are spending of 1.5 hour time continuously in that session.
Fine, fine. Thank you, sir. Thank you.
Thank you. Sir, good evening, sir. Somsekhar, sir.
Yeah, good evening.
Hello.
Sir, can you switch on your video? We'll capture one photograph.
Not one photo, many photo you will take. Thank you.
Okay, sir. Sir, Dr. M. Vamsi Krishna, sir, can you brief about the SAR profile, sir?
Sir, thank you, Gurumesh. Thank you, sir, for accepting our invitation and to present a valuable topic in this gathering. So, thank you. And dear participants, I would like to introduce our today's speaker, Dr. Somsekhar S. Hermat. It is my privilege to introduce today's distinguished resource person, Dr. Somsekhar S. Hermat, professor in the Department of Mechanical Engineering at the Indian Institute of Technology, Madras, Chennai. Hermat sir brings with him over 2 decades of rich teaching and research experience. He has served internationally as a visiting professor at École Centrale d'Inets, France, and at Warsaw University of Technology, Poland, contributing significantly to global collaborative research. He has also held several key administrative and leadership roles, including Director of TANSI, Chennai, Vice President of the IIT Madras Staff Club, Head of the Precision Engineering and Instrumentation Laboratory, Department of Engineering, IIT Madras, and Warden of Alaknanda Hostel. He is currently the Treasurer of the Fluid Flow Power Society of India, Madras chapter. In terms of academic guidance, sir has supervised 33 PhD scholars and has guided over 52 postgraduate students. His research outcomes are highly impressive, with 8 patents, 92 reputed journal publications, 152 international conference papers, 3 books, 3 monographs, and 4 book chapters to his credit. We are honored to have such a highly accomplished academician with us today. Dr. Hermat sir will deliver a session on sensors, actuators, and end effectors in robotics. Please join me in welcoming Dr. Somsekhar S. Hermat sir. Welcome, sir. Welcome to Sri Venkateswara College of Engineering, ATAL FDP program. Thank you, sir.
Thank you very much. I'm audible to all?
Yes, sir.
Yes, sir. Yes, sir. Please, sir.
Yes, sir. Until end, who is there with me? Our Aruna is there with me until end of my talk, or in between she will go?
Vamsi sir, and we both of us will be available, sir.
Okay, we are available, sir.
Okay, thank you.
Vamsi Krishna, sir, and Gurmai.
Thank you. Yeah, thank you. Chennai is fully raining today. Okay. At any time I may disconnect. I'm thinking God's grace up to 9 o'clock, there should not be any issue in the internet. Okay. Okay. Many participants are there, favorite names are there, Our Aruna is there today. Aruna, she is my PhD scholar as well as MTech student. Good evening. How are you?
Fine, sir.
You are joining through your house.
Yes, sir.
Yeah. What is Bindu? Bino is there. What is our Bindu? Or which Bindu it is? Bindu?
No, sir. No. Not our.
Who she is? Bindu Bino. Bindu? No. Ashok Kumar. Ashwati. Many are there. I am very happy. 230 participants are joined for the program. Excellent it is. Very excellent. All are
50 members in YouTube live, sir.
Yeah. Very good. Actually. Bindu Bino, but she is not opening her mouth. Why? Hesitating to talk? You are which college? Our Guru Mahesh, Dr. Guru Mahesh is from which college? Our SC University? Or
sir, SV College of Engineering, sir. SV College of
Engineering. So nice of you. Okay. Many are there, correct? Okay. Shall we start now?
Yes, sir.
Okay.
Yes, sir.
Now I share my slides. Okay. In between, no need to record. Okay. I will give you some of the slides which are useful for you. Okay.
ATAL procedure, we have to record the session, sir.
No, small thing you'll record because I'm taking you to virtual to our lab. You no need. Who told you? The FDP apparatus, 5-10 minutes, you record more than enough. No need to record.
Okay, sir.
Until
you just inform me to, I will stop the recording, sir.
Yeah. Beginning, okay. You are recording now. You have started recording now, correct? Then I will take to my lab. No need to record. Okay.
Just inform me, sir. Then we will stop the recording, sir.
Yeah.
YouTube live also will stop, sir.
Yeah. Very good. Now my slides are visible to you.
Yes, sir.
Yeah. What is first slide? Your slide only. Am I correct or not?
Yes, sir.
Yeah. You are welcome to all participants. Yeah. Let them all, unmute. Whenever they are having any doubts, let them raise or let them share it in the chat GPT. Okay. Your chat box is
already I unmuted all the participants, sir.
Okay. Vamsi Krishna is there until end of my talk. Okay. In between, I will ask you, Vamsi, I am connected or not. In between, okay, every 15 minutes or anything.
Sir. Okay, sir.
Thank you very much, for inviting me for the this talk. Okay. It is a very rigorous course. I am thinking. I have seen all the speakers are there. Many. Hema is there. Many. Our Ravi Shankar sir is there. Many of my very close friends are there to delivering the different talk on robotics. Okay. Very good it is. 1 week short-term course on robotics for Industry 4.0, enabling the smart manufacturing. People now, they all are talking about the smart manufacturing or digital manufacturing or IIoT. Many people, many FDP are conducting all over in India as well as abroad on this topic. Very good it is. Okay. Let the participants will get benefit from this, attending every lecture. Okay. Now, assigned work is for me sensors, actuator, end effectors. Now, previous lecture, Rajya Lakshmi explained about the anatomy of the robots. I hope you have studied about the full anatomy of the robots, which is a prerequisite for your kinematic analysis. Okay. Kinematics is, what will mapping the end effector to the base, correct? Based on the number of joints and the number of links and all what you are doing is. Now what I am doing now is I am focusing more on some of the basics are required for me to explain to you sensors and actuators. And finally, we'll move on to the end effectors. Okay, this is a way how we'll move. Before that, I'll take you to our state-of-the-art laboratory. Now, can you please, stop recording, Vamshi?
Yes, sir. I will stop the recording, sir.
Between you will record it some place. Okay. Now, good, very good. Let us begin with our state-of-the-art laboratory, what we will call the Precision Engineering and Instrumentation Laboratory, which is one of the interdisciplinary laboratory in Department of Mechanical Engineering. It attracts the young and prospective researchers belonging to different disciplines of engineering, mainly the mechanical engineering, industrial production, automobile, electronics and communication, electrical and electronic, computer science, information technology, instrumentation, mechatronics, and robotics. The only one lab where you are seeing the interdisciplinary students are working for their masters as well as the PhD programs. The focused research areas of the laboratories are basically we are concentrating on the 5 major research areas in our laboratory, what you can call a control engineering, mechatronics, robotics, precision manufacturing, hydraulics, and pneumatics. In each category, we are working on the different domains. Okay, if you see these domains, control engineering itself, active noise control, active suspension, embedded controllers, MR fluid dampers, correct machine tool control, position tracking of the many robots, serial manipulator, or a multi-robot agents. Mechatronics, developing the mechatronic approach to the design and development of the precision mechanical systems. Robotics covers both parallel manipulator, underwater manipulator, medical robots, okay, mobile robots, robot calibration facility we are having to calibrate both industrial as well as medical robots, the wireless robot control, the multi-agent systems. Precision manufacturing is another research area where many scholars are working on micro machining, like some of the non-traditional machining process like EDM, electrochemical machining, abrasive jet machining. Now, some of the scholars are now moved towards the hybrid machining process, what you can call electrochemical discharge machining, abrasive hot air jet machining, which is a combination of the 1 or 2 processes to overcome the drawback in the each and other process. For example, if you see EDM and ECM is meant for machining only conducting material. In ECDM, we are clubbing the principle of discharge machining and chemical machining to machine the non-conducting engineering material. Similar to abrasive hot jet machining, which combines the abrasive principle as well as a jet principle, hot air jet principle to machine both conducting and non-conducting materials. Now, these mechanical micro machining methods, we are used to generate the nanoparticles, in which we are very successful in generating the nanoparticles of monoparticle and a hybrid nanoparticle for various applications. Okay. Abrasive flow machining, which is one of the important study of our laboratory, which can be used to modify the surface texture of the many biomaterials as well as to achieve the nano finish. We are using this process to nano level accuracy. Microfabrication to creating the various textures, small structures on the various conducting and non-conducting engineering materials. Okay. Now 3D printing is also one of the major area. Now many scholars are working on the bio-inspired 3D printings. Hydraulics and pneumatics is another area where we worked on many defense projects like a servo hydraulics for the GTRE, electro-hydrostatic actuator for the RCI, hydraulic hybrids for the ETON, micro-hydraulics, piston formers, hyperbaric chamber for the various applications. If you'll see this, my research group working currently on the different domains, mainly first group is working on design and development of sophisticated instrumented experimental setup for micro and nano machining. These setups are used for machining the micro holes, micro channels, micro textures, microstructures. Currently, the same group is involved in generation, characterization, and application suitability of mono and hybrid nanoparticles and surface modification of biomaterials using the laser hydrothermal etching for nanostructured needle-like structures on biomaterials like titanium alloy, SS316, and many materials. Another group working on design, development, and analysis of the fluid power system components like electrohydraulic servo valve for the space applications, including the electrohydrostatic actuator, high pressure and low pressure regulator for the DSSC for space application again. Last but not the least, energy saving systems like a hydraulic hybrid vehicle for automotive applications. Another research group working on the robotic systems. Now, no students are there actually in this robotic system in my group, but 1 or 2 years back, 2-3 students are worked on the robotic system. They are actively involved in path planning, control, and dynamics of the multi-robot, multi-agent systems in structured and unstructured environment, how to control and applying the AI techniques and algorithm in controlling the multi-agents. Last but not the least, some of the current researchers are focusing on additive manufacturing used to fabricate the aero engine parts, automotive and structural applications made of polymers, metallic, and ceramics. Now, all these structures, what we are developing for the bio-inspired cellular structures, mechanical metamaterials based on TPMS parts, and hierarchical structures used for the energy absorption and high-strength applications. All these objectives are achieved through my dedicated scholars. Many scholars are worked on the different disciplines of micromachining, fluid power system, robotics, 3D printing, and surface modification of the engineering materials. What you are seeing, many scholars are worked on these areas. Still, the many scholars are working on surface modification as well as bio-inspired structure printing, nano textures on the various engineering material for the various applications, along with the MS scholars. Some of the popular book we published on their research work, like electrohydraulic